Right now, the chair you're sitting on may not exist, not metaphorically, not as a thought experiment, physically. There is a real, serious possibility that the solid object beneath you, the walls around you, even the body you call yours, are not made of things at all. Some of the most respected physicists on Earth, people who build particle accelerators and write the equations that send spacecraft across the solar system, have quietly arrived at a same unsettling conclusion. Matter might be an illusion, not a trick of the eye, not a philosophical puzzle for late-night dorm conversations, an illusion built into the very fabric of reality itself. Here's the strange part. This isn't a fringe idea whispered in conspiracy forums. It's hiding inside some of the most rigorously tested science we have. Quantum mechanics, information theory, even the mathematics of black holes. Every time scientists have looked closer at solid reality, it has dissolved a little more. Atoms turned out to be mostly empty space. Particles turned out to behave like waves until someone looked at them. And the universe itself, according to one of the strangest ideas in modern physics, might not be a three-dimensional place at all, but something closer to a flat code projected outward like a hologram. So what is actually out there? What is the floor beneath your feet, the light from the sun, the thoughts inside your head really made of? Stay with this, because by the end, you may never look at a solid object the same way again. To understand why physicists started questioning reality itself, we have to go back to the moment science thought it had everything figured out. By the late 1800s, the universe seemed solved. Matter was made of atoms. Atoms were tiny solid balls, like microscopic billiard balls bumping into each other according to neat, predictable laws. Light traveled in waves. Time ticked forward at the same steady rate everywhere. The universe was a machine, and scientists were simply reading its manual. It felt complete, clean, finished. Then, in the span of about 30 years, that entire machine fell apart. First came Einstein, who showed that time itself bends, that a clock on a fast-moving spaceship ticks slower than one on Earth, and that space and time are not a fixed stage, but a flexible fabric that matter can stretch and warp. That was strange enough, but it was only the beginning. A group of physicists then turned their instruments toward the smallest scale of existence, the inside of the atom, expecting to find smaller, simpler versions of the solid little balls they'd imagined for a century. Instead, they found something almost impossible to picture. Particles that didn't have a fixed position until someone measured them. Particles that seemed to exist in multiple places at once. Particles that behaved differently depending on anyone was watching. This new field was called quantum mechanics, and it didn't just update the old picture of reality, it quietly broke it. Because if the smallest building blocks of the universe don't behave like solid objects, then what exactly is the universe built out of? That question has haunted physics for over a century, and the answers that have emerged are far stranger than anyone in 1900 could imagine. In 1801, a scientist named Thomas Young ran a simple experiment that would, without anyone realizing it, plant a 200-year-old time bomb at the foundation of physics. He shined light through two narrow slits cut into a barrier and watched what landed on a screen behind it. If light were simply a stream of tiny particles, he expected two bright lines, one behind each slit. Instead, he saw something else entirely, a pattern of many stripes, like ripples spreading and overlapping in a pond.
Light was behaving like a wave, not a stream of solid little bullets.
That alone was surprising, but it wasn't the strangest discovery. More than a century later, physicists repeated the experiment, this time firing individual particles one at a time, slow enough to track each one. Logically, a single particle going through one slit shouldn't create a wave pattern. It should just leave one dot. Instead, fired one at a time, the particles still built up that same rippled, wave-like pattern, as if each individual particle were somehow interfering with itself, as if it passed through both slits simultaneously. Scientists had a guess. Maybe the particle was secretly splitting or taking some hidden path through both slits at once. So they did the obvious thing. They placed a detector at the slits to watch exactly which one each particle traveled through. And that's when something happened that still unsettles physicists today. The moment they measured the particles, the wave pattern vanished. The particles started behaving like ordinary solid objects again, landing in two simple clumps, exactly what you'd expect from tiny bullets. The simple act of observing the particles changed their behavior. Nobody touched them, nobody disturbed them with force. They were only watched, and reality responded. This experiment has been repeated thousands of times with electrons, atoms, and even large molecules. The result never changes. At the smallest scale of existence, the universe seems to behave differently when something or someone is looking. At all? If ideas like this make your mind spin a little in the best way, this is exactly the kind of mystery we dig into every week here on Cosmos Decoded. Consider subscribing if you want to keep exploring the strangest corners of reality with us.
This discovery split physics into camps that still argue with each other today. One idea, called the Copenhagen interpretation, says that particles genuinely don't have fixed properties until measured, that reality itself exists as a cloud of possibilities, a wave function, which only solidifies into one definite outcome the instant it's observed. Before that moment, in a very real sense, nothing has actually happened yet. Another camp couldn't accept that observation should hold that much power. They proposed something even stranger, the many worlds interpretation. According to this idea, the wave function never actually collapses at all. Instead, every possible outcome happens, just in separate, branching universes. Right now, in this theory, there could be a version of you reading this sentence and a version of you who never clicked on this video at all, existing in a universe splitting off at every possible quantum event since the beginning of time. Neither idea has ever been disproven, neither has ever been fully confirmed. Decades of brilliant scientists have built careers defending each side, and the debate has never been settled. But the mystery goes deeper than particles and slits. In the 1970s, physicists studying black holes stumbled onto an even bigger problem, one that seemed to hint that the entire universe might be built differently than anyone imaged. When something falls into a black hole, all of the information about it, its mass, its structure, every detail, appears to get crushed down and stored not throughout the black hole's three-dimensional volume, but smeared across its two-dimensional surface, like writing on the skin of a sphere, rather than data filling its interior. That detail might sound technical, but the implication is enormous. It suggests that the universe might not need 3 full dimensions of space to store all of its information. A flat, two-dimensional surface might be enough to encode everything that happens inside a three-dimensional volume, the same way a flat hologram, when lit correctly, can project a fully three-dimensional image. This became known as the holographic principle, and it didn't stay confined to black holes for long. Some physicists now seriously propose that our entire universe, Galaxies, stars, planets, you, might be a three-dimensional projection generated from information encoded on a distant, flat boundary, the same way a hologram creates the illusion of depth from a flat piece of film. If that's true, the three-dimensional world you experience as solid and real would be something closer to a very convincing projection generated from a deeper layer of information we cannot directly touch or see. And this isn't the only place the idea of information keeps appearing where solid matter used to be. The physicist John Wheeler, one of the most respected minds of the 20th century, proposed something he called it from bit. His argument was radical, that every particle, every field, every force in the universe, every physical it, ultimately derives its existence from answers to yes or no questions, from bits of information. Reality, in his view, isn't fundamentally made of matter at all. It's made of information, and matter is simply what that information looks like when something interacts with it. Around the same time, computer scientists and physicists began asking an uncomfortable question from a completely different direction. If information can generate a convincing three-dimensional reality, could that reality be artificial? Could it be generated, simulated, the way a video game generates a convincing world from nothing but code running on a processor? The philosopher Nick Bostrom formalized this into something now known as the simulation argument. His reasoning was simple, almost mathematical. If civilizations can eventually build computers powerful enough to simulate entire conscious universes, and if even one civilization anywhere ever does this, then simulated universes full of simulated conscious beings would outnumber the one real original universe. Bostrom never claimed to prove we are in a simulation. He only showed that if certain plausible assumptions are true, the odds tilt strangely against the universe you're experiencing being the base reality at all. None of this has been proven. None of it can currently be disproven either. And that's exactly what makes it the most engaging, unresolved mystery in modern physics. We have rigorously tested evidence that something is deeply strange about the foundation of reality, quantum behavior that depends on observation, information that behaves like the true currency of existence, a universe that might be projected from a flatter, deeper layer, but no one yet agrees what it actually means.
So why does any of this matter, if it's still unproven? Why should it change how you think about your life today, on solid ground? Because the implications, if even partially true, reach into every corner of how we understand existence. Consider physics first. If the universe truly is fundamentally informational, if particles are patterns of data rather than solid stuff, then the search for a theory of everything, the long-sought goal of unifying gravity with quantum mechanics, might require a complete shift in thinking. Instead of asking, what is everything made of, physicists may need to ask, what is everything computing? Several serious research programs exploring ideas like digital physics and computational cosmology have already begun treating the universe less like a machine made of matter and more like a process that's running, calculating its own next moment, frame by frame, like a simulation rendering its world in real time. Consider the nature of space and time next. If the holographic principle is correct, even in part, then the three dimensions you walk through every day are not the most fundamental layer of reality. They're an emergent result, generated by something flatter and stranger underneath. That would mean space itself, the very stage on which your entire life takes place, is closer to an output than an input, not the foundation of reality, but a kind of display. Now consider humanity's place in all of this. For most of history, every culture has asked some version of the same question. Is what I'm experiencing actually real? Ancient philosophers in Greece imagined people chained in a cave, mistaking shadows on a wall for the whole of reality. Thinkers in India and East Asia described the physical world as a kind of veil, a temporary illusion layered over a deeper truth. These were once treated as mystical, untestable ideas, interesting to ponder, impossible to verify. What's remarkable now is that modern physics, working entirely through mathematics and experiment, independently arrived at eerily similar territory, not through philosophy, not through religion, through particle detectors, black hole equations, and information theory. Two completely different paths, ancient intuition and modern measurement, converging on the same unsettling possibility, that the world we touch and see might be a projection of something deeper, not the deepest layer itself. And then there's the future. If we are, even partially, inside an informational or simulated structure, the long-term implications for technology are staggering. Understanding how reality renders itself at the quantum level could one day inform entirely new kinds of computing, communication, even propulsion. Technologies built not around matter and energy in the traditional sense, but around manipulating the information underlying them. But perhaps the most personal implication is simpler than all of this. If reality is, at its deepest level, built from information and observation rather than solid, permanent stuff, then the line between observer and observed, between you and the universe you're looking at, may be far blurrier than it feels. Your attention, your act of looking, may not be a passive window onto a fixed world. It may be, in some small but real sense, part of what brings that world into being. That's not mysticism. That's where the equations currently point.
So look around you again. The chair, the light through the window, the weight of your own body. None of it has stopped being real in any way that matters to your life today. You can still touch the chair. You can still feel the light on your skin. Nothing about this changes how solid your morning coffee feels in your hands. But underneath all of that familiar solidity, physics has pulled back a curtain it didn't expect to find, and what's behind it doesn't look like billiard balls bumping through empty space. It looks like information, patterns, probabilities that only become real the instant something looks closely enough to ask. Maybe one day a more complete theory will resolve all of this, and the strange quantum behavior, the holographic hints, the simulation arguments will simply be footnotes on the way to a deeper truth we can finally picture clearly. Or maybe the truth is that reality was never meant to be pictured at all, that the universe runs on a layer of existence so different from chairs and light and bodies that our everyday language will never quite capture it. Either way, one thing seems certain. The universe you think you know, solid, fixed, simply there, was never the whole story. It was only the part of the story rendered clearly enough for you to see.